Hello everyone, my name is Andrei, and in this course with my colleague Mikhail, we're going to introduce you to particle physics. If you start worrying already, what does particle physics have in common with machine learning, don't panic much. The topic we have selected will be very well related to machine learning and data science. I'm team leader of Yandex School of Data Analysis at LHCb Experiment. Along with scientists from other universities across the globe, we are working on particle physics problems. Our group focuses on applying machine learning to those problems and topics of this course that are pretty much grounded on our experience. We are especially fascinated by the fact that such research field as particle physics, hunting for answers to profound mysteries of our universe, heavily depends upon machine learning techniques nowadays. There are also clues that such connection goes a bit deeper, and you can draw parallels to other scientific domains as well. So the course is structured in the following way. At the first part, I will give a mild introduction into particle physics and will explain basic notions so you will understand the structure and the main terms that physicists use to describe the forces and particles that comprise the fundamental level of our universe. At the second lecture, we will explain some of the details how particle detectors are designed and what mechanism can be used to detect different kinds of tiny particles. At the third lecture, we will explain how new physics search can be mediated through a search for rare processes. Then we'll show some examples of dark matter search at proposed experiment at CERN. And at the final, the fifth lecture, we will show how machine learning techniques can be applied to design of the new experiment or upgrade existing detector. So all of those 5 lectures will be a mixture of domain knowledge and machine learning. Hopefully the curricula will help you to appreciate how specific techniques of machine learning can be used to help improving precision, accuracy and speed of data processing that happens at fundamental physics. So why are we focusing on particle physics? First of all, it faces the most fundamental problem of our universe, and understanding of those problems will explain the mechanism of our world so we can appreciate better where we are and how the place is structured. Ultimately, this knowledge can enable people to improve our level of existence by transferring the knowledge into technologies that we use on a daily basis. There are plenty of puzzles that are still unsolved, and advanced machine learning can be applied there. Such exercise does not necessarily require domain knowledge, so we hope you will find the theoretical part not very demanding and practical part of our course engaging and rewarding. A short disclaimer that we are not particle physicists, and particle physics is a subject essentially much more complex than described here. We do not guarantee completeness, accuracy or applicability of the information therein to your particle physics adventure. The sole reason for these simplifications is to allow for a more prominent universe picture to emerge that will help you to get engaged in the beautiful journey of our universe exploration. Let's start with a variety of scales you can encounter there. As you can imagine, there is a fundamental level at which particle physics works. There are quarks or tiny bits of matter that stick together to form a more significant objects like a proton or neutron. As those attach to each other, an atomic nucleus is formed, then goes a whole atom that turns into a molecule and then to a regular matter that we use to interact with. Going further, we get into celestial kingdom. We encounter astronomical objects like planets, stars, nebulae, and galaxies. The observable universe today is enormous. It is still a spherical thing with a radius about 50 billion light years long, or about 5 to 10^26 meter long if you prefer a metric system. You may wonder why the scale is so different for different objects, and what is the reason for such a difference. So, one of the answers to this question is that different forces mediate different objects. On this slide, we show which forces are responsible for the creation of different kinds of objects. It starts with so-called strong force. It is responsible for dealing with subatomic objects like baryons, like protons and neutrons, or atomic nucleus. Then there is electroweak force, that is a mixture of electromagnetic and weak ones. It deals with a higher scale ranging from atom to matter. And then there is a gravity. Of course, that is responsible for creation of much larger objects that we know from looking at the sky through the telescopes. Those are ranging from asteroids to galaxies. You can see the magnitude of those forces differ significantly. The strong force is way stronger than the gravity. There are 41 orders of magnitude difference between those two. These differences make physicists' heads spin quite a bit. We will touch this as a question in a second after introduction of the Standard Model. Standard Model of elementary particles. The Standard Model describes what the universe is made of and how it holds together. It rests on two central ideas. The first one, all matter is made of particles. And the second one, that these particles interact with each other by exchanging other particles associated with the fundamental forces. The essential grains of matter are fermions, and the force carriers are bosons. The names of those two classes refer to their spins. Fermions have half-integer values of spin, whereas bosons have integer values as shown on the slide. Fermions come in two families. The lepton family has 6 members, with electron being the best known of them. The quarks family contains 6 quarks. The up and down quarks are found inside protons and neutrons. The 12 fermions are the building blocks of matter. These particles interact with each other through fundamental forces. Each force comes with one or more force carriers. Strong force mediates through gluon and binds the quarks within protons and neutrons. The photon is associated with electromagnetic interaction. The weak interaction is responsible for radioactivity. It comes with Z and W bosons. Combining elementary particles allows for creation of more complicated forms of matter. There are rules how quarks can be connected in a more complicated particles, hadrons. It is where the Large Hadron Collider takes its name. The 3 quarks combined may form a baryon, for example, proton or neutron. Even number of quarks, like 2 or 4, form a meson. Until the beginning of this century, it was thought that mesons come only in the form of quark and anti-quark pairs, but in 2007, Bell collaboration has discovered tetraquark that has been confirmed by LHCb collaboration in 2014. The Standard Model is both remarkably simple and very powerful. Complex equations are expressing all possible particle interactions mathematically. These equations allow theorists to make exact predictions, and nearly every quantity that has been measured in particle physics laboratories over past 5 decades falls right on the predicted value within experimental error margins. At this slide, you see a snapshot of a lovely animation that grasps the spirit of the standard model by a bunch of Lego building blocks. If you have a couple of spare minutes, I highly recommend having a look at it. So, what are the standard model shortcomings? There are things that it does not explain well or does not explain at all. For example, gravity is not included in the standard model at all. And the question, why is gravity so much weaker than everything else? The second question is why masses of particles differ so massively. Standard model misses a great deal of the universe. It is known that there are 5 times more dark matter that sits in the galaxies around us, and standard model have no clue what kind of particle it consists of. Also, the standard model does not explain the asymmetry of flows for matter and antimatter well enough. We know that there are vast amount of matter exists in the universe around us and almost no sign of antimatter. So this asymmetry cannot be explained by current version of standard model.